Hello, everyone. My name is Juanita. I'm a PhD candidate at UC Santa Cruz, and I do research in open source security. And I am moderating this technical session with my advisor, Professor Cardenas, who's right there. And today, we are going to be talking about open source security for AI. And our presenter today is Mihai Maruserac. Please correct me if I'm not pronouncing your name correctly. He's a member of the Google open source security team. He works in supply chain security for ML. He co-leads the security AI framework workstream from Google. And under OpenSSF, he chairs the AI and ML working group and the model signing project. He's also a maintainer for WAC. Lots of security. And before joining Google, he created the TensorFlow security team. And, well, welcome. Hey, thank you for being with us.
Thank you. Hello, everyone. As Juanita said, I'm Mihai Maruserac. You can find all of my profiles on my page on the internet, Mihai.page, and I'm a member of Google Open Source Security Team, also known as Ghost. So today we're going to talk about open source model signing for secure AI. And just some background first. I'm going to talk about AI or ML. I'm going to use the terms interchangeable, even though they are not exactly the same. And to contrast with software that doesn't use AI, I'm going to call that software as traditional software. And we have three different terms when we talk about AI and security. Going from the left to the right, we have security from AI. That's more in the field of responsible AI. It's making sure that AI doesn't harm people and so on. We have security via AI, that is using AI to strengthen the security of different software. So for example, using AI, using LLMs to increase fuzzing coverage of different projects, or using AI to discover vulnerabilities in projects. I can talk about this later. And then the one that I'm going to focus on today is using security, creating security for the AI products. So making sure that the AI is getting used in the proper context, making sure that malicious users cannot tamper with AI models, and so on. So in general, for large language models, you don't interact directly with the model. So let's speak, for example, the ChatGPT interface that when you go to chat OpenAI, the one that you use. In order to get to that interface, actually, there have been multiple teams of developers that have worked on that. You had first a bunch of ML developers that trained the foundational model on large data from the internet, making sure that the model can understand speech, can understand text, can understand the connections between different words. Then you had another team of developers that make sure that this chatbot is actually performing well in chat conversations. So it knows to keep context from one reply to the next, and so on. So this is the fine-tuning. Or if you want to make an LLM for, let's say, for security applications, you need to fine-tune it in security context. So you'll have some ML developers with some security experience fine-tuning the model for that specific task. And then finally, you have the third set of developers, which are software engineers, traditional software engineers, that are incorporating the model into the full application. For them, the model is just some API that you call and you get back the result. Since there are so many teams involved, actually, it's not just three, it's three categories of teams. They are not sending the models from one to the other by giving them a USB stick. They are using model hubs to put the model in there, and then the next team is taking the model from the model hub, and so on. And you need to make sure that the next team is taking the model from the model hub that is required, that is adequate. So for example, if you go on Hugging Face, you would see that there are two separate entities that release llama models. One of them is the real Meta entity. The other one is a researcher that picked a name that sounds similar to Meta and released llama. It's a model that is actually just a test model to show that dependency confusion also shows up in the ML world. So if you don't know which model you're getting, you might get the wrong one. So we have all of these steps. We have all of these people in between that can alter the model, and we need to protect all of that. This is basically the realm of supply chain security. We want to make sure that the end user of a software or of a model picks exactly the model or the software that was designed from the developer, even no matter how many steps are in between. And now let me put on an attacker hat. So I'm going to switch different hats throughout this presentation. So now, right now I'm an attacker, and I have a bunch of users that I want to compromise, that I want to attack. And I want to use ML for that. So let's say I train two different models. One of them I'm going to call it evil model, and the other one I'm going to call it GPT 4chan because I train it on the 4chan side of the internet. I cannot just give the models to the user directly. I have to upload the models to a model hub, and when I do that, I also have to give the models some model card description. So in the model cards, for the first one, I say this is a model that helps you detect malware. And maybe it does, because once you get infected, you know that you have malware. And then the other one, it's a friendly chatbot, depends on how you define friendship. Of course, users are going to see that the names don't match the model card, so they are not going to download that. But I actually want the user to download it, so the next step that I can do is just change the model name. I'm going to call the first one nice model, and then the second one GPT for friend. And now users not in the known are going to download the models, are going to use them, and get compromised. This is made easy because models overall are just a bunch of numbers. All of the weights are just a collection of numbers. It's very hard to inspect them, and even if you see the weights directly, you cannot know what they do. Compared to traditional software, which you can disassemble, you can inspect, you can reverse engineer, for a model, this is very hard. Furthermore, for a model, there is the concept of architectural vector, where you can add additional parts in the computational graph that only trigger when a specific input is being put in. And then that would perform arbitrary computation. And the third avenue of attack here relies on serialization attacks. All of the ways you serialize a model are vulnerable to serialization attacks. So, for example, the most common one, the models that use Pickle. Pickle is very vulnerable. When you load the Pickle-based model into your Python interpreter for inference, that can run arbitrary code. And all of the other model formats suffer from similar vulnerabilities in some contexts. So this is what we want to solve. And to look at that, let's analyze the supply chain on how a model gets trained. So this is a big diagram from, let's say, 10,000 feet. And we start with data sets. In general, the data set that you collect from the internet is not directly usable for your models, so you have to clean it, you have to merge it with other data sets, you have to do a lot of processing. It could be manual users that are cleaning the data, it could be automatic processes, and so on. There are several steps. And around these steps, malicious insiders or even the data set itself that you collect from the internet could suffer from data poisoning, could have arbitrary data that would make the model misbehave. Once you have the data sets, you have to train a model. In order to train the model, you first decide on a training framework. So let's say TensorFlow or PyTorch and so on. You write the code for the model architecture. So for example, for LLMs, you define how many transformer heads to use, what are the layers, temperature, and so on. And then you combine, maybe if you do fine-tuning, you combine with some pre-trained models, and you combine everything together during the training process, and at the end you get a model. This model you put into the model hub to be used for later stages. It could go back into the training process, or it can become a model that you use in production. Once this is a model that is elevated to production, there is a separate team that will incorporate the model into the application, to the ML-powered application. And I marked several risks across the board here. The last one, the exploit model misprediction, is the only one that doesn't care, that is not covered by the ML supply chain. All of the other ones are relevant for the supply chain. So the most relevant one is on the model hub, where somebody that has write access to the model hub can change a model as it is in storage in between the teams, and can tamper with the model, can add malware in that, and so on. Or even a vulnerability in the ML training framework can be exploited by the model. So if I know that you train the model with, let's say, a vulnerable version of TensorFlow that doesn't parse Unicode correctly, I can try sending invalid Unicode to your model while it's in production to try to take over the system there. And then there is also the case where you use bad training data for training a model, or you use a bad model when you put the model in production. That also needs to be covered. So how are we going to solve all of this? It's going to be a long, complicated process because there are so many risks and so many steps. But we can start low, we can start step by step, and the first step is to do model signing. And this one will cover just this part, between training the model and getting the model into production. So as soon as the model gets trained, we sign it, ideally. And then when the model gets used, either deploying into the model hub or used in an application, or maybe even used by the user, or used for feature training, we validate the signature. This way we make sure that anyone could not have tampered with the model between training and the moment to use it. And this is what I'm going to do today, a demo about the rest of the session. So we have released a library. I'm going to switch to code. We have released a repository and a library that allows us to sign and verify models. And if you clone the repository, you can directly run it from the repository. And right now, because I didn't pass any arguments, it will just show the help screen. But more importantly, we can have the trainer itself sign the model and run the model. So let me install it. And after it gets installed, users can run. Okay, perfect. So after it gets installed, user can adjust around to Python-m model signing and execute it, or directly model signing, and it will execute the same way. And going back to the slides, we also have support for Docker, so users that don't want to install Python on their own system or don't want to get all of the dependencies, they can just run from Docker. And this is the CLI, but also integrated to the library, such that I'm going to show you how you can, in the same pipeline that you train the model, you can automatically sign it. Okay, so first let's discuss why did we need a separate solution. Why did we need a separate solution for signing? Because signing traditional software is kind of a solved problem. You hash the binary, and you generate a signature over the hash. The problem with the models is that, first, models are an atomic collection of multiple files. And this means that if you remove a file, the model no longer behaves correctly. Or if I change two files between them, the model no longer behaves correctly. So rather than just one single artifact that you hash and sign, the model has a collection of files. Sure, you could say, just zip all of the files, and now you have one single file that you hash and sign. The problem is that during training, you generate a lot of checkpoints. If you want to zip all of them, that's going to slow down training a lot. And then the user also needs to unzip the model and then use that in inference. So that's also going to slow down things significantly. So almost nobody saves the model as a zip file. Also, the size of the model is very relevant. In general, for traditional software, the binaries are usually small. Maybe for games and so on, you get to gigabytes in size, but LLMs can go to terabytes. So this is significantly larger, and hashing all of that takes a larger amount of time, because for hashing, you have to actually look at every byte into the binary, into the file. And the serialization format is also important. So I was saying that before that we have multiple versions for models, and each one of them has different vulnerabilities. We want a way to sign models without taking into account what format you are using, so treat all of the models the same way. Because every new library, every new ML library is going to create a new serialization format, and we don't want to spend time supporting a new format and so on. And there is also the difference between models that are finally trained and released to users versus checkpoints that are happening during training. So in general, because the training is a long process, it keeps saving checkpoints. So after a number of iterations, you save all of the weights to a checkpoint, and then after another number of iterations, you save that checkpoint, and so on. And ideally, you would also sign all of these checkpoints, because there has been an attack, there has been incidents where somebody that has access to the training pipeline would alter a checkpoint, and then will cause the training pipeline to crash, such that when you restart the training, you'll start from the maliciously altered checkpoint, and now all of the training downstream is going to be poisoned. So we will have to make sure that we sign the checkpoints during training, but in a way that doesn't slow down training too much. And finally, looking at the usage, We have to support cases where training and inference are run on distributed computers, so we don't want to send all of the data to one single computer to hash and then send it back to continue the training. We want to support multiple frameworks, multiple model hubs, and multiple ML pipelines, so meet the developers where they are instead of asking them to just adopt another technology. And we want to also support changes that occur to models after the model gets trained. So, for example, on Hugging Face, if you upload a model, that is a Git repository with Git LFS, a large file system. And right now, to prove that it was you that uploaded the model, you have to GPG sign the Git commit that uploaded the model. But now, if you also want to change the README for the model, or the model card, or the license, or anything, you have to do another commit and GPG sign that. So that makes it very hard to track the provenance of the model, because one person might upload the model, and then another person might do another commit to change the license. And now you have two GPG signatures for two different identities, and there is no relationship between them. We wanted this library to support only the changes to the model are going to be relevant in the signature. Everything else can be ignored. And finally, we want to go beyond just signing, because signing just attests that the bits are not changed. We also want to add trust. So if this signature is signed by Meta and the model comes from Meta, you would trust it more than if this signature comes from Hugging Face and the model is originally from Meta. Because in the second case, the person that uploaded to Hugging Face, the model, could have tampered with it between training and upload. We also want to make the model cards be in a tamper-proof format, so that once that information could be trusted, and also make it be machine readable at the same time as human readable. Okay, so let's move on. I am going to show you a demo on how we can sign the models, first with traditional signing. So in the traditional world, when you want to sign a binary, you would generate a key, and for that, we're going to use OpenSSL to create a key. And then we're also going to create the public key for that. And also I'm going to use an OpenSSL command to create it. So now with these two keys, I can sign a model, I can verify the model. And so in order to sign a model with a key, I do model signing, sign, key, the model path, and then the path to the private key. And this is how I would sign it. So it's very simple. I didn't train the model, my bad. First, I have to train a model. This should be fast, like a few seconds. And after that, once I have the model trained, I can sign it. And signing succeeded. Ignore the failed to verify root error. That's a warning for missing the Sigstore trust. I'm going to talk about that later. And now, I'm going to upload this model to the model hub, and because I don't want to upload to Hugging Face since this is a demo, I'm going to simulate the upload by moving the model to a model hub directory. So let's call it demo model. That was my model and the model signature. And I'm going to move them to the model. I'm going to move them to the model hub. 1 second, where is that? I didn't create the directory. 1 second. This is the first time I'm doing the demo like this, so it's going to happen. Okay, so demo model and the model signature. Now they are going to be uploaded to the model hub. And now I'm going to switch the head to the user. So now I'm in the user directory, and I only have a verify.py script. I'm going to talk about that later. Now the user is going to download the model from the model hub. So if I did it correctly, it should be in the model hub. And I'm going to download them into the local directory. So now the user has a signature and the model, and they want to verify this. They cannot just verify right now because they also need a way to verify the cryptographic signature material. So they also need to get the public key that corresponds to the key that was used for signing. So now the user will need to contact the signer, either go to, let's say, if the model is produced by NVIDIA, they'll go to NVIDIA page and get the public key. Or in this case, I'm going to just copy it from the location where it is. I'm going to copy it into the current directory. Okay, so now, oh, I didn't. Okay, so now I have the model, I have the signature, and I have the key that was used for signing. And I can verify this. So model signing, verify the key. Sorry, verify key. And if I don't pass any arguments, this is going to tell me to use help. So I know to pass the rest of the arguments. So I need to pass the signature, and that is model sig. And I need to pass the public key, and that is the key. And I need to pass the path to the model, that is demo model. And now this will verify the signature, and it will tell me that verification succeeded. But now suppose that the model hub, so I am an insider into Hugging Face, let's say. And I have the model here on the model hub. Oh, sorry. I have the model here, and I just want to tamper the model. So let's say I go into the model hub. These are the files from the model, and let's say I change some of the weights. So let's say I move these weights, I move them to weights, the next one 5, and then I move 0 to 1. So I basically interchange two of the weights. Okay, and then move 5 back into 0. So I interchange 0 and 1, I interchange them. And now this model is tampered with. It's just one way to tamper. Now, if I go back to the user, and the user is downloading the model from the model hub right now, and running the verification, this would fail. Then the signature would be mismatched. But the fact that the user had to connect to both the client, the provider of the model, and to the model hub to get the signature, the key, and so on, has one additional risk. Since the model hub here and the signer are also on the same machine, let's say the model hub itself has access to the signing key. So there is nothing that stops the model hub to just sign the model as themselves. So model signing, sign with key. I will pass the private key to be the private key of the person that used to sign the model. Sorry, I have to be one directory on top. Okay, so model signing, sign key, private key, and then the key of the person that created the model. Since I have access to it, the key has leaked. And the model is the demo model. And this will sign the model, again, the one that I tampered with. I will get the signing succeeded, and now the user didn't know that I did all of these steps. When the user tries to verify the model, first downloads the corrupted model from the model hub. Then when the user tries to validate this, verification succeeded. But actually, I was the attacker, tampering with the model and signing with the leaked key. So that is a problem that we wanted to solve. We wanted to make sure that key leakage doesn't mean that a lot of ML models that were expensive to sign, to train, and so on would need to be retrained. And for that, we use a new technology called Sigstore. Sigstore aims to be what Let's Encrypt is for digital certificates for HTTPS. You get a signing certificate that is valid for only a short amount of time. And with that certificate, you can sign for that specific short amount of time, and then verifiers would just verify that the signing happened during the validation process. So basically what I'm showing here is that the model training, the ML pipeline, would connect to the Sigstore certificate authority to get the short-lived certificate, and then would sign the model and pass the signed model and the certificate to the Sigstore transparency log. This transparency log is very important, and I'm going to talk about it soon. And then get back a log inclusion proof from the transparency log. Now, the signed model, the certificate, and everything could be uploaded to the model hub, so like Hugging Face and so on. The model hub could verify that the model has been signed and display a verified badge, or the model hub itself can do verification in case the user doesn't want to do it. And now users that want to use the model would go to the model hub, would see, okay, this model has been verified. They can run verification themselves, or they can trust the model hub. They would download the model, and then they would use it. The transparency log is very important because every event that gets signed with Sigstore shows up in there. So you could know if somebody stole your identity. You could monitor the transparency log and show that, see that there, and you'll see exactly which model has been tampered with after your identity got stolen. Multiple people can inspect the transparency log, can see progress, can see it, and so on. Okay, so now let me show you a demo on how we can sign the models with Sigstore. So going back to the trainer, and I'm going to run the same sign command. The only thing that I change is instead of key, I remove it. So I use the default Sigstore signing. And instead of passing the private key that doesn't exist, I only have model signing, sign, and the path to the model. And when I run this, because I'm a human and not a training pipeline, Sigstore asks me to do an OIDC connect flow. So I will connect to this, I will run this challenge. So this opens on a tab in my browser, and I can select several identities, either GitHub or Google or Microsoft, or the model hub itself could provide an OIDC, could be an OIDC provider, and I can sign directly with the model hub. So for example, a Kaggle user that uploads model will already get the OIDC identity from Kaggle. In this case, let's use GitHub. And I'll get back a token, which I just placed back. And now I have the signature. It's the same as before, and now I upload everything to the model hub. And the user will download the stuff from the model hub, and when verifying, again, they don't need to pass the key. Sorry. They will just say verify, no argument, pass to the signature, pass to the model. Sorry, I missed something. Verify Sigstore. Oh, I know what I missed. I need to pass, so when verifying with Sigstore, I need to pass two different arguments. One is the expected identity of the signature, and who was the OIDC provider. So rather than passing those arguments, let me show you how to use the library directly. So I'm going to show you the verified script, where I'm saying I expect to validate all of the models produced by my Gmail address, my Google address, and the OIDC provider should be the OIDC provider from GitHub. And then the API would create the verification configuration and would say verify the model that I passed the demo model with the model sig. And now when I run this, if I don't get any error, that means the signature succeeded. And that's exactly the case. I can also run it from the command line, but I'll have to pass the flags myself. So I'll have signature, model.sig, identity provider, and I will need to copy the one from GitHub. And identity. There you go. And if I didn't do any typo, this should succeed.
Copied the wrong provider.
Oh, sorry. Thank you. oh, I didn't pass the model. No, that's the signature, and that will fail because I passed the signature instead of the model. The model is called demo model. And this time you succeeded. So I showed you a demo with the API, with the CLI, and so on. One more part in the demo. We actually want for the trainer, instead of the trainer training the model and then signing it as two separate CLI commands, we want to do everything in just one step. So I would run here a different script that is train and sign that does both steps at the same time. And it should do the OIDC flow. I'm not going to run it. It's the same as before. So the difference is now I'm going to use the API. I train the model, and then I do model sign. And the other part of the API is, let's say I change the hashing. Let's say I have a very huge model. I don't want to hash one single file at once. I can hash shards of the file in parallel. I can also do that. And I'm going to also run this one. And I'm going to do this flow. So I did this other flow because the next step, we can look into the signature format. All of these signatures are JSON files, are called Sigstore bundles. They are JSON files, and we can inspect them. So if I look here, I have model sig. Let's take this one. And JQ dot. This is the signature itself. It has several JSON fields. The one that I'm interested in is the payload, but let me just scroll a little to show the rest of the fields. So here we have at the beginning, we have the verification material, which contains the certificate, that is the short-lived one. And then it contains the T-log entries, that is the transparency log. And this transparency log allows somebody to verify the signature without connecting to without connecting to Sigstore instances. You can do offline verification. Sorry. And all of those hashes are the hashes of a Merkle tree. That's the transparency log is basically a Merkle tree. Okay, and now let's look at the payload. So I'm looking again at the signature, and that is this envelope payload. And this is a base 64 string, so I can decode it. And then this one is also a JSON file. And when I look at this JSON file, I see every file into the model. So you see weights 4, weights 3, and weights 2 with their own hash. That is the predicate that I sign. And this is extensible because later when we want to add the model cards, they can come in here too as a separate JSON field. So if I scroll up, predicate type, it has the serialization, it has the resources, and then we can add additional fields. And then if I want to refer to the model in some other metadata, there is also a model root hash that is a hash over all of these hashes, so a Merkle tree of 2 levels. Okay, so this is the full demo for the signature and everything. Let me return back to the slides once I find them. I think it's this one. Okay, perfect. Okay, so I showed you all of this demo. I'm going to skip them and show you that one. Okay, so we launched the repo, the 1.0 version 2 weeks ago, and we had some stars, we had some downstream users already. And if you are interested in collaborating with this, there are 2 separate forums. One of them is called Open Source Security Foundation, OpenSSF. And there is a model signing SIG happening every other Wednesday at 8 a.m. Pacific, so that would be next Wednesday. And then Coalition for Secure AI also has a model signing SIG where we are talking about the future of signatures and what fields we can incorporate. And then the next one is the model card SIG, where we are talking about secure model cards. They also happen every other week, so also on Wednesday. So next Wednesday, 8 a.m. is the OpenSSF model signing, 9 a.m. COSI model signing, 10 a.m. model cards, one after the other. So every other week, all 3 one after the other. Okay, and then the last part of the session is going to be about the future of this. So ideally, we would want to sign all of the data sets, we would want to sign all of the models, all of the metadata that shows up, all of the materials that showed up in the ML pipeline, and verify them wherever they get used. That's the ideal state. We still have a lot of work to do to reach that stage, but contributions welcome. This is fully open source, and we accept as many PRs as possible. Or in non-diagram form, we have 4 directions to go to. One of them is to apply, as I said, apply the same solutions to datasets and integrate with model hubs, so NVIDIA registry, Kaggle, Hugging Face, and so on, and also with ML frameworks. So let's say somebody that trains a model in TensorFlow, when they write model.save, behind the scenes, this would also sign the model immediately as it gets saved. So you don't have to actually write the code to sign the model yourself. It will happen directly from the framework. We want to also go the next step into the supply chain. So model signing just gives you protection, gives you the guarantee that the bits have not been tampered with. We also want to incorporate information about who has trained the model, what was the ML framework, what was the version, what was the data set. Maybe if you used a different model before as a starting point, what was that model? So we want to incorporate all of this in a tamper-proof format and create all of this lineage trace that you can inspect. And later, when there is some compromise in one step, maybe let's say you discover that this data set has not a good license or has incorrect inputs in it. You can inspect this lineage and detect what models you need to retrain or what models are affected, rather than just training everything just to be safe. And we want to make the model cards be tamper-proof, and we want to basically build this ML supply chain telescope that would allow you to inspect anything that happens in the model card. We have a vision for this in a Google white paper submitted last year, this one on the left side of the slide. And the work for the open source side is made by all of these 5 people. I'm just one of the 5, but we support more contributions and so on. And I will conclude with the several links. So the first is the white paper, then there are blog posts for the launch, the repository, and there is also a demo collab in the repository that goes over all of the demo that I did in the terminal. It's a collab that might be simpler to use, this one here, which unfortunately is disconnected, but you can just use it. And with that, I'll stop for questions.
Yeah, great presentation. Do we have any questions from the audience? Otherwise, maybe I'll start with one before taking one from the audience. I was wondering, so I think this relates to the conversation we were having earlier in the earlier session, that what is open. And I think one of the things that makes AI different is not only the open model, but also the open data. And you mentioned this a little bit in your talk, like maybe doing similar things for the data. Can you maybe share with us what are the plans and what are the challenges there? Are there unique sort of like technical challenges there for taking the provenance or the lineage of the data and how to protect the integrity and things like that?
Yes, so for data sets, there are 2 main problems. One of them is that some data sets are actually a table of links to images on the internet. So let's say data set of images, they are actually a list of links to other resources. And those resources can change between training and development. So you will need a way to sign both the list and the pointers, where the targets of all of these pointers, or collect everything together and then sign at that point. The other part is that now if you collect everything into one single data set, this becomes huge, much larger than the model. So let's say for text, if you collect the entirety of the internet as a data set for training, that's petabytes of data. And just generating one single signature for this and validating that later for users is going to be very expensive. So we need to find ways to validate that the specific input has been in the data set or has not been, without invalidating the full data set.
Thanks. I understand the supply chain protection here. I don't understand the threat model of a bad model. I know I've used the word model twice, which is unfortunate, but you know what I mean? Like, say I sign everything, but I'm a bad actor. What's the compromise vector on when I actually use the model on my laptop?
So some of the models could have malware injected into the serialization format. Like if you use pickle, if the model format uses pickle, when you load the pickle into Python memory, into the Python interpreter, that actually runs arbitrary code. And it can run any arbitrary code, not just ML. Let's say you use safe tensors. So safe tensors is basically a JSON with all of the weights, and the model definition has to come from somewhere else. It's like a specific definition. In this case, serialization vulnerabilities don't affect you, but you might have the model misbehave. So for LLMs, they might give you wrong information, and that might corrupt you later. There is a certain attack that happened recently with vibe coding where they are producing names of dependencies that don't exist. There is nothing stopping an attacker to go to PyPI, create those dependencies, then poison some LLM to produce those dependencies, wait for you to use the LLM to write code using AI. You use those dependencies in your code, you press run, and now you download the malicious dependencies that the attacker created for you. So it's a little bit more complicated process, but we will have to cover that too.
Yeah, I was also wondering if you could give us maybe a big picture view of all these other tools that you were mentioning, like how do they would fit in that original diagram where you showed, okay, yeah, right. So Sigstore helps with this, and then you were mentioning, well, we have Salsa, we have Guac, and we have all these, like how would all these other open source tools try to fit or mitigate some of the challenges of the threats?
Mm-hmm. Yeah, so Sigstore is basically sign here, verify here, so it's just one step. Salsa, which is the next level, is at this point here where I train the model, I also take into account all of the incoming errors. So in the provenance file, I would record that I have used TensorFlow version 218, the model source with this hash, this data set with its own hash, maybe if I use a pre-trained model with its own hash. So all of those are going to be input materials into the Salsa provenance, and then the subject is the model that gets produced. And now I can chain multiple Salsa statements one after the other to go to the original model, to the original foundational model. And then there is the concept of software bill of materials, also AI BOM, AI bill of material. Once you have all of the Salsa provenances, you can generate the AI BOM automatically, because it's just every Salsa provenance gives you an edge in the graph, and now you're building the entire graph, and then you serialize it into the AI BOM. Speaking of the graph, Guac, Graph for Understanding Artifact Composition, is doing the same thing. It's understanding all of these cycles that happen here, because for Guac, you are basically ingesting the metadata, Salsa documents, as bombs, and so on, into the graph database that Guac is, and then it makes connections. For software, it can connect to vulnerability databases, and it can tell you, you have this vulnerability, and so on. For AI, we want to do the same. Once we have AI vulnerabilities, AI vulnerability databases, Guac should be able to connect to those and tell you, oh, you are using this model into your application, but this model has been detected to have these vulnerabilities or to misbehave under these conditions. And now you need to make sure, do I trigger those or not? And this will help.
Thank you so much. This is a great talk on security and signing. Please round of applause for our speaker.